Operating a blast furnace is a constant battle against physics and chemistry. Today, we are breaking down the key operational challenge that operators face every day and the solution that keeps this giant reactor running. So, let's begin with the most prime important thing, raw material. First up, a deceptively simple problem finds. These are teeny particles smaller than 5 millimeter that seem insignificant but can cripple an operation. The problem is twofold. They block the spaces between the large particles, drastically reducing gas permeability, and they tend to segregate, concentrating in area where they cause most trouble. The negative effects are severe. They block the flow of the reducing gases, leading to inefficient iron production. They accumulate on the furnace wall, forming destructive scaffold and scabs. And in the worst cases, they can even appear as a solid scab right in front of Tuyere, threatening the entire processes. Next, the invisible enemy moisture. Any water entering the coke or the ore burden is not just a harmless steam. It's a massive heat thief. This moisture must be evaporated in the upper furnace, which steals immense amount of energy and lower the temperature profile or isotherm within the shaft. This delays the critical reduction process. The consequences, the reduction zone is pushed lower into the furnace, making it less efficient. This forces more direct reduction to occur, which consume excessive amount of costly coke and cools the furnace. Most of it can trigger a viscous condensation cycle where moisture evaporate in the center only to condense on the cooler walls, driving the process further out of balance. Now let's talk about the rhythm of the furnace. Modern descent. When this becomes unstable through hanging and sleeping, the entire process is jeopardized. The mechanism is a three-act drama. Hang breezes of semi-molten ore form in the cohesive zone, as we have discussed many times in our earlier presentation, supporting the weight above. Voiders. Meanwhile, coke beyond these breezes is consumed, creating a hidden cavity. Slip. The bridge suddenly collapses due to continuous consumption, violently disturbing the carefully layered structure inside. And what is the result? The gas flow is shattered, ore is insufficiently reduced, and the furnace rapidly chills. The solution is not quick, it requires operating on reduced blast volume for 5 to 10 hours to partially and patiently re-establish the stable layers again. Now, speaking of the gas flow, our next challenge is channeling. This is when the reducing gases, lazy by nature, finds a path of least resistance and simply bypasses the bulk of the burden. It's caused by gaps from the irregular descent, concentration of fines, or poorly melting material. Operators spot it through key indicator: a sudden drop in CO utilization, number 1, a dip in blast pressure and localized hotspot on the steps. So what is the fix? The short term, they might check or vibrate the burden to collapse the channel. Long term, the only cure is stable burden descent, and perfect burden distribution is the best way out. Some enemies come from within. Alkalis and zinc enter the furnace in a small amount but recirculate with a vengeance. Alkalis like potassium and sodium can recirculate 3 to 10 times their input. They catalyze coke degradation, form a scaffold, and attack the furnace refractory lining tremendously. The zinc often from its source from the recycle scrap vaporizes and condenses in a similar cycle. It also forms a scaffold and critically makes refractories brittle, threatening the furnace long-term life. Control is straightforward in theory. Limit their inputs and remove them via slag for alkalis or through the fine dust evacuation or extraction from the zinc. Now, those recirculating elements often end up here as wall adherences. We have two main types of scaffold, which are solid materials stuck to the wall, and scabs, which are burden material that haven't fully melted. Their location tells us the cause. In the upper furnace, it's typically high alkalis, zinc fines, and low temperature. In the upper furnace, it's often resolidified slag. The remedies are equally distinct. For upper furnace scaffold, a cleaning action involves lowering the burden level to let them fall off. For lower furnace scaffold, you need to melt them away with the coke blanks and lower slag basicity. Now, down to the business end, the 2 years. This is where the action happens and where failures are most dramatic. Blockages from the unmolten material can cause coal to back up and ignite, leading to explosion. This is why Tuyere cameras and pressure sensors are critical. Tuyers themselves can fail, burning out from the hot metal attack or tipping from the weight of a scab above. And perhaps the most dangerous is a water leak. Signs are subtle, a dull glow, a small a smell of ammonia, a spike in the top gas hydrogen, but the consequences is catastrophic. Uncontrolled cooling and refractory damage. It also costs in terms of outrages of the furnace. Now, perhaps the ultimate test of the operational skill is managing the furnace stop and start. A stop is not a pause. The cohesive zones solidify, heat consuming reactions continue. The restart is a race or to remelt this frozen heat or hot. The pitfalls are clear. Too fast blow in cause channeling, too fast PCI restart risk blowpipe explosion, high slag basicity lead to solidification, and so many. The solution is a master class in the preparation. Charge extra coke before the stop, use fluid slags, and follow a meticulous gradual restart procedure. Patience is the key to speed here. Finally, the outlet, the cast house. When things go wrong here, production stops completely. A chilled hearth is a nightmare scenario where the liquid flow from the tuer to taphole freezes solid. A recovery is a major operation involving oxyfuel lances, coke blank, and ultra fluid slag to reestablish the connection. A coke mess is the less catastrophic but just as disruptive with excessive coke flowing out of the taphole. The response is to immediately reduce wind volume, plug the hole, and find the root cause, be it poor clay or water leakages. So, in today's world, we cannot ignore our environmental footprint. The blast furnace route is a major source of CO2, emitting around more than 2.3 to 2.5 tons per ton of steel. The primary contributor is carbon input from the coke and coal. The industry is fighting this by maximizing coal injection, using top gas efficiency, and CO injecting natural gas or hydrogen. But there is a thermodynamic limit. For step change reductions, the industry is looking to new processes like direct reduction coupled with electric arc furnaces. To win these battles, operators rely on an arsenal of advanced instrumentation in bud and probe to monitor drying, to your camera for real-time visibility, infrared top cameras to see gas flow patterns, radar profilometers to map the burden layers, pressure taps for process stability, moisture gauges for real-time compensation. This is the never and ending process, and these are supposed to be the main nerve center of modern blast furnaces. So, what are the key lessons? Stability is paramount. It all comes down to smooth burden descent, a steady gas flow, and a balanced heat budget. Quality in, quality out, controlling raw material finds, moisture, and chemistry is the first and best line of defense. Too proactive, not reactive. Advanced instrumentation allow you to see problem before they escalate. And finally, think in the system. A problem in one area, like hanging, often has its root cause in another, like poor burden distribution. The furnace, the blast furnace operators is the master of this complex dynamic system, constantly working to maintain its delicate balance.